Hello everybody and welcome to this geometry nodes tutorial in Blender 5.0 using the new volume grid nodes, new-ish. It's been a while since they came out actually. But nonetheless, we're going to be making this 3D smoke with geometry nodes. So let's get into it. The basic structure of this whole thing is that we're going to have a simulation zone here represented by this cube. Then we've got an emitter, which is going to be Suzanne. They've got their own geometry nodes networks that I'll explain. And basically we're going to set up a domain, which is going to be this cube, just subdivided into a bunch of little voxel cubes. And then we are going to do something really similar to the 2D fluid simulation tutorial that I had a long time ago, where we're using a couple different fields, velocity, divergence, pressure, and then a density field, which we're actually calling smoke here. That's smoke. The smoke field is what you actually see, and then we're essentially creating forces, enforcing incompressibility in the fluid, and watching the density or the smoke evolve over time. So that's our basic setup. We have our initialization here, we have our simulation here, and then a little bit of post-processing, just removing grids, making the voxel data structure slightly more efficient before we bake so that our baked output can be as small in memory as possible. So first things first is our domain setup. First thing we're going to do is create these simulation grids. We're going to do that with the volume cube node just to create an initial volume. We're going to use the inputs from our parameters node group, which is also right out here. So the reason we create a node group like this is just so that we can reference these sort of global values that we want in multiple places without having to drag a bunch of noodles around. So we create that volume cube with the min and max bounds that are defined in our parameters node group. In this case, I think it's just -2 to +2. And then also using the solver resolution, you can press Control H to hide or show all the different outputs of a specific node group. That's why these are actually the same, but they look different. And so the solver resolution, we're going to set to just something relatively small, like 64 in this case, so that if I do turn off the baked output with M for just masking that, then we can still run this relatively quickly. If we go down to something like 32, it'll run faster. But anyway, 64 is fine. And then the cool thing about that is that if I simulate the solver resolution at 64, what we're going to do later is we're going to use the smoke resolution at a high resolution so that you get more detail and you don't see all these little blocky cubes here. But the cool thing is I can run at this like relatively interactive rate where, you know, when it bakes, I can see it running as fast as it will in the final render. And then that will give me a really good idea of what the higher resolution output will look like, and I can illustrate that by just unmasking the bake node, and you can see that the shapes match up pretty much perfectly. It's just in the 64 version where the smoke resolution is also 64, it looks more blurry. So working this way will give you an idea of what your effect will actually look like without taking forever to bake, because it takes a lot longer when you bump up the smoke resolution is something like 256, like 128 or 256. Okay, so create a volume cube. We get the density, which is the default grid value or grid attribute or whatever you want to call it that it creates. We're going to remove that because we don't need it. We're actually going to call it smoke. We're going to voxelize the grid. And the reason why we're doing this is that the underlying data structure for these volume grids is called OpenVDB, and it will do some memory optimization where contiguous blocks of voxels that are adjacent to each other that have really similar values will be just referenced as one thing with their own individual bounds. And that's all well and good, but for what we're doing, we want all of the voxels available so that we can calculate the like divergence and pressure and enforce incompressibility in the way that we want. And we just don't want any of that optimization right away or during the simulation. And then we'll use the topology from that voxelized grid to initialize all of the other grids that we need for our simulation. So we've got velocity, divergence, and pressure. Velocity is a vector grid. The other two are float grids. So we just use this field to grid node, which will take in the topology input, which will define like what does the grid that you're creating actually look like in terms of its bounds, like its minimum and maximum points, as well as the topology of the voxels. So in this case, it's just a bunch of voxels at the resolution that we set here. But in other cases, it could be optimized voxel topologies like we just talked about. So now we have all of our grids in the same topology, and then we're going to add our smoke grid. So the way we do that is, the reason we're doing this separately is because we're going to want it to be a different resolution. So here, press Control H. Instead of having solver resolution, we use smoke resolution. And right now I've just got it set to 64 so that we have like an interactive frame rate. But if I set it something higher, like 128, and it's going to take longer to simulate here, but you can see how you get a little bit more detail. And so you can just ramp that up to get more and more detailed smoke with the same solver resolution, which is really cool because then you can, like I said, get that really good idea of what your simulation is going to look like before you actually spend the time to bake out a whole high resolution output. So yeah, you can see, that looks a bit better than the 64 version. But right now, we'll set it to 64. Ultimately, for the final render, we'll actually set that to 256, which is quite high, and will take a long time to bake. So we'll do the same thing. We'll get the density grid, we'll remove it, we'll voxelize it, we'll multiply it by 0 just so that its smoke starts at 0 because it's a float grid and we don't want any smoke to start out with. We'll add that during the simulation. And then we are done with the initialization. Now, before we jump into the actual simulation loop, I want to talk about the emitter. So we're using Suzanne for the emitter here. And really all we're doing here is we are taking the geometry, we're moving it in this like random way. Here, I'll show you without the simulation on. So we're just moving Suzanne around in this kind of random way, driven by these two noise textures, one for the position and one for the rotation. And then we're using this simulation loop to store the last position and new position so we can get the differential in our simulation node group so that we can use that velocity to drive the forces that the smoke that gets emitted by this emitter initially have. So as Suzanne like moves around, she kind of pushes the smoke and it plumes out in a cool way. It's just what I like. And yeah, so you can do whatever you want. But the details here of how this kind of works is we are subdividing the surface because I haven't done that before. So yeah, and then we store the original position of Suzanne right here and just put that into the simulation loop. And the reason why we're doing that is we don't want to like iteratively apply the randomized transformations because then Suzanne kind of might like float away out into the sky or down below the sea. And instead, we kind of want it to act like there was no simulation group, but we need the simulation group so that we can iteratively, through each frame, store the new position and the last position. Okay, so then each frame, we take that original position and then we transform it by this, which just takes these two noise textures that are driven by the scene frame and tuned a bit and scaled. So this is all just tuning, and then we convert this bottom one to a rotation because that controls the rotation. This is translation. We combine that into a transform the original point, and before we transform the actual Suzanne geometry by that randomized transformation, we'll store the position as an attribute called last position. And then we transform it, and then we store that new transformed position as the new position attribute. And that's it. Then we're just going to set shade smooth and set the material for our Suzanne, and that'll be for rendering. Okay, so turning back our simulation node group on. The first part of our simulation is adding smoke. So what we're going to do is, here, we'll take in our emitter geometry, and then we're going to just add smoke near it. So we're going to sample the nearest point for each voxel grid, and if we're going to sample the position of the nearest point, and if the distance from the position of our current voxel position and that position is less than this amount, then we're going to add a certain amount and scale that just by 2 to the smoke that we already have. And so here we get the name grid smoke, and then you can just like use the math nodes on that to add a little bit to that grid based off of the position of the voxel. And then you just store that again with a store named grid in the same name. So smoke. And then we've got our addition of smoke to the simulation. After that, we're going to add velocity, and that's where what we did in the emitter node group comes into play. So basically it's the same sort of thing. We're going to apply velocity to the velocity field that will affect the smoke near the surface of Suzanne based on the new position and last position that we stored in the emitter node group. So working backwards, we'll start with getting the velocity grid. Then we're going to add a little bit of velocity to that based off of distance from Suzanne and the new position and last position, and then store that back into the velocity grid. So to make sure that the velocity that we're adding is only near Suzanne, we're going to scale whatever velocity we're adding by the distance of the voxel position from the closest new position of Suzanne. So the new position is the position this frame, because that's how we stored it before. So that's the same as the last node group, and we're doing less than a different value, so 0.025. I'm just tuning that to my liking, and then multiplying by 2.5. Again, that's a scaling factor that you can tune as you like. So for the actual velocity that we want to add near Suzanne's surface, what we'll do is we'll take, we're sampling both the new position and last position from the closest point on the surface to the voxel grid. And then we're subtracting, we're subtracting the new position, or sorry, we're taking the new position minus last position. So subtracting the last position from the new position, and that got a vector from the last position to the new position, an arrow pointing there. We scale that by 0.5 because this is, again, a tuning parameter. And then we're adding a little bit in the z direction just so that the smoke kind of floats up, or it starts by going up. And that's also just something that I liked. You could totally take that away if you wanted. Again, then we're scaling that velocity by the proximity to the emitter. And then we're adding that to the original velocity, or the existing velocity field. And there you go. That's how we add velocity. So the next step is pretty important, and it's advecting the velocity, which makes the velocity carry itself through space over time. So the velocity is going to affect itself. So similar to before, we're going to get the velocity named grid, and then we're going to store that after some transformations. And what's going to happen here is we're actually going to sample the velocity field at the current voxel index to get the velocity that currently exists. And then we're going to subtract that velocity vector from the position of the current voxel, and then sample the velocity field again at that offset point, and then we're going to just set that as the velocity at the current point. So it's like, okay, if we're moving this way, then we look back a little bit and we just bring the field to where we're currently at, and that is the advection, which just means moving a field through space over time by velocity. And so that's what we're doing. We sample the grid index at the voxel index. So this is just the XYZ index of our current voxel. And we're sampling velocity there. So that's our velocity that we currently have at our current voxel. And then we're subtracting that from the position of the current voxel. And then we're sampling the velocity grid again at that new offset position. And then we're using the field to grid node. I don't even know if we actually need this. We definitely do. That is because, we need it because we have a field from the sampling of the grid. So we're not existing just in grid space. Geometry nodes and the way they've implemented this does some implicit conversions, but it doesn't. It works if you're using like math nodes, like if I just like took this grid and multiplied it by 2 or scaled it or something like that. But if you're working with fields, which you'll definitely get from doing the sample grid index or sample grid node, then you'll have to convert that back to a grid using field to grid. And we'll just use the same topology as velocity because we don't want it to change. And then we will bring that offset velocity back into the current velocity, and that's how you advect velocity. There is an advect node, like a volume advect node, but I find it doesn't work the way that I want it to. And maybe I'm doing something wrong. Let me know if I am. But I've done quite a bit of testing, and it tends to be a little wonky. But anyway, let's go on to calculating the divergence. Now, so like what happens is after the velocity advection, the fluid or the density the fluid might compress or expand, but real fluids are incompressible, so we want to enforce incompressibility. So we want to calculate the divergence to know how far off we are from an incompressible state, which would have 0 divergence. And so the way that we're going to do that is we're going to look at the 6 different neighbors. So we're getting I'll do an overview first, and then we'll see how it's implemented in the notes. So we're going to look at the 6 neighbors of the current voxel. And we're going to get the velocity at each point. And then for each axis, we're going to, so x, y, and z, we're going to subtract that, get the difference. And then we're going to normalize by the sort of like voxel size. In this case, we're just assuming the voxel size is 1. So divide by 2 because it spans 2 voxel spans. And then we'll store that in the divergence. You could also just use the, the grid divergence node. And in this case, you can't assume that the voxel size is just 1. Because under the hood, this will account for this actual size of the voxel depending on the bounds. And so since our min and max bounds are -2 to 2, that is 4 units. So what we would do is we do 4 divided by the solver resolution, and then multiply that by the divergence that comes out of this grid divergence node. And then we would just like pop that in here instead of using this whole network. So I put that in there just so you can see how that might work. It's a lot easier, a lot simpler, but in my testing, it didn't look as good. It just didn't keep all of the detail. I don't really know why. So I'm just doing it the manual way. And so the way that we do that is we use these get value at offset vector nodes. So it's just getting the value at offset, and then it's a vector output. And so what we do is we take the current voxel index, and then we add the offset that you input as parameters to the node group, and then we sample the same grid at those offset indices, and then you get the value of the grid that you input. So in this case, we're getting the value of the velocity at offset positions, and we just go for x in the positive and negative direction, and then positive and negative for both y and z. And then for each of those, we're subtracting the negative direction from, or the negative offset direction from the positive offset direction. And then we're adding those all up, and then we're dividing by 2 to normalize by the voxel size. And then we use the field to grid with the topology from velocity, and we're storing that back in the divergence. So that's how you calculate the divergence, because if you think about it, it's like in the x direction, like just think in one dimension, you are subtracting the amount coming in from the left side, from the negative x offset position, from the amount going out, or yes, going out from the positive direction. So in the negative direction, a positive value means negative divergence because it's coming in to the voxel. And a positive value on the positive offset side means positive divergence. So instead of adding them together, we actually subtract the negative side because if it's negative, then you want to add divergence because it's going away outside of the current voxel. So that's why you subtract for each of them. You just do that for each dimension, and then you just need to divide by 2 because it normalizes for the span of the voxel sizes between the positive offset and the negative offset. And there you go. That's how you calculate your divergence. So now we have the divergence at each point, but we need pressure. And the reason we need pressure is because divergence is sort of like local to the actual voxel. But pressure, you calculate for the whole field. And so we do this in an iterative way. And it uses the divergence over a series of iterations. In this case, we're doing 16 to figure out how much pressure is coming in or out, or like pulling or pushing, compressing or decompressing from any given point in the voxel grid. And then after we calculate the pressure, we can get because that's just a scalar value, we can get the gradient of that, which is a vector, and then subtract that from the current velocity field to push the velocity field into a place where when you calculate the divergence, you get 0, which means the fluid is incompressible. So subtracting the pressure gradient, it's also called the projection step, but subtracting the pressure gradient helps to enforce incompressibility. So first, to get the pressure gradient, we need to calculate the pressure. So we're going to use a repeat zone to do whatever iterations you want to do. In this case, we're just doing 16. And within each pressure iteration, we're using another get value at offset node. In this case, it's just for a floating point, which is why it doesn't have that vector suffix. So again, in each direction, positive, negative, y, positive, negative, z, positive, negative. And so we're getting the pressure at each of those offset points. This is the same setup as the previous node group. And then you add those all together. You convert to a grid. And then you subtract the divergence from that. And then you average. So you divide by the total number of voxels that you're sampling the pressure from. And so to gain some sort of intuition for why this works is that the adding of all of the neighboring voxels' pressure and then ultimately averaging them sort of spreads out the pressure, so you get this sort of like global influence to all the different voxels. And then we subtract the pressure or the divergence from that because the pressure will counteract the divergence to enforce incompressibility. So if the divergence is positive, we want the pressure to be negative. We want to pull in. And if the divergence is negative, we want the pressure to be positive and push out, so that when we ultimately subtract the pressure gradient in the direction that the pressure field is increasing, and we want to subtract that, then if the divergence is positive, it'll make it more negative, and if it's negative, it'll make it more positive, and it'll push it towards that 0 stable incompressible state. And so after we do our iterations to try and converge on the actual pressure, which we may or may not get to 100%, but it's okay because we just care about it looking good in this situation and not being totally physically accurate, we can move on to subtracting the pressure gradient. So what we need to do here is we just need to get the pressure gradient and then subtract it from the velocity field. So this is another situation in which there is a dedicated node for getting the grid gradient that you could use. So I have it up here. But again, when I tested it, it just didn't look as good. Like there was like little details, like a little sharpness that was somehow lost. So It's here if you want to try it, but you can also do it the long way. It's not that long. But yeah, you do the same thing where you do the span of the domain size divided by the resolution of the solver, and then scale the grid gradient that you get out of the grid gradient node by that. So you'd get the gradient of the pressure, scale by that, and then this is your pressure gradient. So the way that we calculate that here is we're going to essentially get the gradient in each dimension, x, y, and z, and then combine those into a single vector. So what you do is you get the value at offset, which we've seen this node group before, of the pressure at each positive and negative direction for each dimension, like we've done before. So you subtract the negative offset position from the positive one for each one, and then that gets the difference of the pressure from positive and negative in each dimension. And then you just combine that into a vector. So the x difference for x, y difference for y, z difference for z, and then that's your pressure gradient. So convert that to a grid because it's a field at this point. And then we're just going to subtract that pressure gradient from the velocity field and then store that back in the velocity. And we have improved and tried to enforce incompressibility, which is what we really need. And then the last step, the very last step, is advecting the smoke. And so we've advected the velocity before, and the basic principle is you just take the velocity at the given point, and then you sample whatever field you're trying to advect at the position of the current voxel offset by the velocity of the current voxel. So again, there's like an advect grid node that you could use, but it does weird things, and I ended up not using it, but again, I have it here just in case you want to use it. The long way is also not very hard, and the way that that works is we want the smoke grid because that's what we're advecting. We also want velocity because you need the velocity to advect any given grid. So we're going to sample the velocity grid at the position of the current smoke grid point. And then we're going to subtract that from the position of the current smoke grid point. And then sample the smoke grid at that offset position. And then convert that from a field to a grid. And then we're going to multiply by 0.96 just so that the just so it dissipates a little bit over time, so the smoke kind of like fades away instead of just staying around forever. And then you store that back into the smoke grid. So this does a little bit more than just advection. It also does this this fading, but mostly it's smoke advection. And then that's it. That is it for this node group. I'm going to turn back on the baked version just so we can play it. And the last thing that we do is just a little bit of saving, or like pruning and baking and some cleanup. So let me go over that. So the last things we're doing is we're just setting the material so that we can control how it looks in the render. We're removing grids. So I'm removing the velocity, the pressure, and the divergence. So all we have is the smoke. And one reason for that is if I pop in a viewer node, right now what you're seeing is you're going to see the smoke grid. But if I don't remove the grids, you might see something different. Okay, the reason why it switched back is because it's I haven't pinned that view, so you're not seeing the viewer. But if I turn that back on, you can now see that without removing the grids, right here. Let me just duplicate this, and then I will ungroup it, and then I'll put this in here so we can just operate at this level without issues with deactivating this viewer node. So I got this viewer node on. If I remove all these, then we get our velocity, or our smoke grid, and we can see it. But if I don't, then you might see something else. So in this case, you're seeing the pressure grid, but like you can barely see it, so you don't really see anything here, but it is there. And then same for velocity and everything else. Like I believe that this is, you can see like some tiny green because like with a vector grid, you'll see the X, Y, and Z for red, green, and blue. But anyway, so it'll get confusing if you have all these grids and you pop it in a viewer node and you can't see anything or see what you want to see. So just remove all of the different grids that you don't actually want to see. This is also important for the baking step, because what you don't want is to have a bunch of grids, especially at like higher voxel resolutions, that are getting baked and stored, because that's a lot more memory that you're eating up, or disk space. So remove them for efficiency's sake, as well as visualization. So I'm just going to go ahead and delete those. And then also we're going to prune smoke. So that OpenVDB memory optimization that we talked about at the beginning comes into play here. So the pruning the grid is just pruning it by a certain threshold, which we set at 0.01. So if the value of this smoke grid is below 0.01, we prune that grid, and then it gets optimized so you don't store it in memory. And so we store that back into the smoke grid. This won't affect the simulation now because we're outside of the simulation loop. If we did this in the simulation loop, then when you advect it, it might pull from like this one spot. It gets weird. And so we just do this at the end, and then we go directly into the bake node. And this is where we can bake our high resolution output so that we can see what we see here. In terms of the rendering, if I Shift-Alt-Z to turn off all of the overlays and we go Z and up, this is the render that we've got. This is like what it's going to look like. I'll just go to this frame, 77. I like that frame. If we go to the shader editor, you can see that the material for the smoke is just a principled volume. I have this color set to this purple color, purpley pink lavender color. You can set it to anything. Excuse me. And then, yeah, ooh, that's nice. I like that green. Oof. Man, maybe I will play with it a bit here just to show you what you could do. Like, let's set it to this green, maybe a little darker. And then for the emitter, we also have our material that we set in at the end of our geometry nodes network. So here, this is just a metallic texture, super simple, with a roughness of 0.1. And if we wanted to edit the color to work with something here, maybe a bluish green, more blue than green, more yellow. Maybe something like that. And then we'd want to do the same thing for the background color. Maybe something like that, and then darker or lighter. Ooh. Not too dark and not too light. Colors are always finicky. Man. I mean, I like that too. You can also do contrasting colors. Ooh, that looks terrible. I mean, that's kind of interesting, but a little funky. Getting it too bright. I don't know. We don't want to spend so much time just messing around with this, do we? Like the brightness there. And then let's go back to that frame. Yeah, I don't know. I mean, you could see it. I like having a darker background. Let's see if we darken that up. Ooh, interesting. I don't know. Okay, well, I'm not gonna bore you with this and like make this video super long just because I'm playing with colors at the end. But you get the idea. We're just gonna actually change this back to something like blue or green, make it dark. And we're gonna turn up this to be a bit lighter. I want this, yeah, okay. There you go. That'll be pretty good. And then yeah, so mess around with that, change it however you want, and I think that's it for this tutorial. So I hope you enjoyed this tutorial. I hope you learned something, and above all, I hope you had fun. Until next time, bye.